Up until this point in the chapter, we've taken a look at how two variables affect each other. They're either direct variation, in which they both move in the same direction, as one increases, the other increases, or they're an inverse variation, when one increases, the other one decreases. Well, today we're going to take a look at combined variation and joint variation. Sometimes, oftentimes in life, there's more than one variable at play. Sometimes you have multiple independent variables, and they can affect a dependent variable both in an inverse and in a direct way. So consider Major League Baseball. Consider the Cubs. I love the Cubs. Now consider how they go about winning. Well, their batting percentage, or the amount of times their guys get on base, has to be directly related to their winning. The better they hit, the more runs they score. The more runs they score, the more they win. But it's got to be inversely related to how good their pitchers are. And that's called their earned run average. The lower your earned run average is, the better off your team is. So their winning formula might be both a combination of direct variation on their batting average and inverse variation on their earned run average. Now, another type of variation we're going to talk about is joint variation. And this is one in which a quantity is directly related to two or more independent variables. However, it's not inversely related at all. So let's take a look at a few examples. In our first example, we read that a bicyclist is pedaling at 85 revolutions per minute using a front gear with 39 teeth and a back gear of 13 teeth. At this, she's traveling at 21 miles per hour. Now, we want to describe how her speed would change when she decreases to 60 revolutions per minute. So this is a combined variation equation where speed is directly influenced by the revolutions and the number of gears on the front, or number of teeth in the front gear, but inversely related by the number of teeth on the rear gear. So let's go ahead and substitute in. We have 85 for our revolutions, we have 39 for our front gear, and we have 13 for our back gear. So our speed is 21. K is what we're looking for here. This is 85 times our front gear of 39, all divided by 13. Let's start to get K by itself by multiplying both sides by 13. As a result, I'm going to end up with 273 is equal to K times 85 times 39. Now I need to divide both sides by the product of 85 times 39. And when I take 273 and divide it by 85 times 39 in the bottom there, I'm going to get a resulting K value, or constant of variation, to be 0.0824. Now let's use that out to the fourth digit there, and let's rewrite our formula. Speed here is inversely related to 0.0824 times the number of front teeth times the revolutions times the number of front teeth divided by the number of teeth in the back gear. Now we are asked to consider how our speed changes when we reduce our revolutions to 60. So let's find our speed when our revolutions are 60. Our front gear still has 39 teeth divided by 13. Now when I enter all that into my calculator, I find that my speed is going to come out to be 14.8 miles per hour. Now we want to know how much our speed was going to change. So we were traveling 21 miles per hour. 21 take away 14.8 reduces our speed by 6.2 miles per hour when we decrease our revolutions per minute of that front chainring from 85 down to 60. All right, in our second example, we have again another combined variation equation. We see that the hyperfocal length h in yards varies directly with the square of the focal length L in inches, and inversely with the selected aperture for our camera. We want to write a general variation equation to model this situation. So we see that h varies directly with the square of the focal length. So k times L squared. L will be our focal length in inches, and then inversely with our selected aperture. we'll let the letter A represent aperture. Now we want to find a value for the unit of K, our constant of variation, when our hyperfocal length of 1.75 inches, that's for our L, is 12 yards, that's our H, and the aperture is set at 9. So let's go ahead and set up the numbers that we have. 12 is equal to K times 1.75 squared, all divided by 9. I'm going to start by multiplying 9 to both sides to get it out of the denominator here. 9 times 12 gives me 108. 108 is equal to K times 1.75 squared. Now I'm going to divide both sides by 1.75 squared to get K by itself, and this will leave me with the value of K to be 35.27. Okay, now I can rewrite my variation equation from part B there, including my constant of variation. So this should read H is equal to 35.27 times L squared, all divided by my aperture setting. All right, now we want to apply this variation equation here. It says find the hyperfocal length needed in yards, so we're looking for H here, if you want to shoot with a 12-inch lens, that's our value for L, and with an aperture setting of 2.5, that's our value for A. Okay, so let's go ahead and substitute some numbers in here. We have 35.27 is our constant of variation. We're going to multiply that by our length of our lens here in inches, 12 squared, and then divide that by our aperture, 2.5. We can plug all of that into our calculator at once, and we'll get a hyperfocal length of 2,031.5 yards. All right, now let's take a look at a joint variation equation here. We're going to go about solving for this in the exact same way here. So we want to find the volume of a solid with a circular base. It varies jointly as the height of the solid and the square of the radius. So we're going to say our volume varies jointly. Now that means it's a product of the height and the square of the radius. So that's K times H times R squared. Now let's go ahead and substitute some numbers that we know in. If the volume of a solid is 47.1 cubic inches, when our radius is 3 and our height is 5, so we're going to substitute 5 in here, and then 3 squared. We want to go about finding our constant of variation here. So that's 5 times 9, which is 45. I need to divide off that 45 from both sides. And K will give me a value of 1.046. All right. So now we can rewrite that joint variation equation to read as volume is equal to 1.046 times the height times the radius squared. All right, now what geometric solid is this? Going back to geometry last year, you have a circular base. It's a volume of a solid, so it might look something like this. You guys should probably know that as a cylinder. All right, we got one more to go here. In this final example, we see that A varies directly as B and inversely as the square of C. So is this combined or joint variation? Now, let's go ahead and start off by writing that. We got A is equal to K times B divided by C squared. We know some values of B, C, and A. This will help us find our value for K. So let's substitute those in. We have negative 6. K times negative 8 divided by 2 squared. Now 2 squared is 4, so we have negative 6 is equal to K times negative 8 over 4. Negative 8 and divided by 4 is negative 2. If I then rewrite negative 6 is equal to K times negative 2, divide both sides by negative 2, my K value is 3. All right, now we're ready to rock. A is equal to 3 times B over C squared. Go ahead and substitute the value of 4 in for B and negative 2 in for C and find the value of A.